So we'll be talking about non-destructive testing or indirect testing. And as a first step, I would like to point out a few key features in comparison to the traditional way of testing, to the direct or so-called destructive measurements. I just pitched a couple of images there just to give the idea of you can visualize drilling a core and crushing a sample in order to get a strength, or we'll see some other ways of doing it. Old school method for finding a reinforcement and PT ducts, breaking, visual inspection. Other way of doing it. Is there a better way of doing it? Are they outdated? The answer is no, basically. There's no point in being a partisan of one or the other team. The key point for a professional, for an inspector, is the best combination of both in order to extract the maximum amount of the information. So if I should point out some key features of one family versus the other, I would say that a direct traditional measurement, I measure directly the quantity I'm interested into. And normally I destroy a sample for doing that. While the non-destructive or indirect approach focuses on measuring a related quantity somehow correlated with what I'm looking for. By definition, a direct measurement is typically certain, calibrated. It has, it can be a certificate with a huge number of decimals behind, make you certain that the quantity is measured. While with non-destructive testing, we are rather dealing with qualitative or comparative information. A key limitation or a key feature is that if I test one point, if I break open one location, I have a full perfect insight of that specific point. How can I be sure to extend that insight can be assumed for the whole structure? That is the role of NDT. Okay, so we mentioned that there is generally some related quantity that we measure. That basically defines the measuring principle of each measurement. So as a short classification by physical principle, just prepared a couple of qualitative slides. Electromagnetic waves analysis, that's a very technical term, but it collects a number of different measurements, and among which, and now let me get my pointer, yeah, the first and most important inspection. A good inspector keeps his eyes open. You have to really provide a subjective judgment on a location. Well, if I shift myself from the very narrow window of wavelength that my eye allows, I notice that I can shift toward X-ray analysis or lower frequencies. I will enjoy thermal camera and infrared inspection, or even lower frequency with GPR. All have in common this basic principle. If I keep an eye on the sonic waves, there's a world of testing that can be done, and we concrete guys are strongly related to the metal guys that use the same similar principles with very high frequencies. You play by seeing how your body reacts and responds to a sonic impulse. Can be very high frequency, can be this average frequency that it's our bread and butter in concrete when we measure ultrasonic pulse velocity, cross-hole testing, PROCEQ, and whatever. And similar approach, but low frequency, brings us toward testing of the so-called hammer sonic testing, typically done on masonry or large structures or pile integrity testing. Other methods are typically electrical in nature, and we'll see that especially for corrosion. Electrical process will need electrical tools. So this is our electrical toolbox where we find the rebar location, we induce currents, or we measure potential, we measure resistivity, we measure polarization resistance, electrical quantities. Or, and in the last box, I put myself the mechanical quantities. I can measure rebound, I can measure the hardness of a structure or even the metal by measure the amount of the energy that is transferred into the body. And so we measuring a rebound distance or a rebound velocity, or we can measure the amount of penetration that a specific probe can reach when projected on with a given energy into the surface, or we can measure the force needed to pull out a specific insert. In all these cases, we are dealing with a mechanical quantity related to the final quantity, which is concrete strength, in this case, to be measured. Okay, so this just as a warm-up, but probably more interesting is a classification by application. Now we'll be picking up from the different boxes of physical principles the tools we need for our specific purposes today. Specific purposes that we'll be talking about are the structural detail, but broad terms for highlighting geometry and even embedded objects and defects of a given structure. A key point for a structural engineer is the estimation of the concrete strength, and for durability and life service estimate of a structure, the corrosion investigation. And let's dive in with the structural, well, some of the measurements we'll be talking today. So we'll be talking about the rebar location, ground penetrating radar, and shear wave tomography for structural details. Then I picked the two most important ones at global level for concrete strength, which are hammer testing and ultrasonic pulse velocity, and some mention of the electrical method for the corrosion. So let's start with the imaging technique, structural detail assessment. All these techniques provide an image, a visual insight of what's inside an object. And let's start with a general overview of all three of them. Rebar location. Rebar location, we'll see, it's the gold standard for steel rebars, the one typically accepted for measuring accurately cover, estimating diameters. We'll be touching the ground penetrating radar as its key feature of being the most versatile locator. It extends locating capabilities not only to steel objects, but to metal, but to plastic and voids also. And the most recent technique, which is the ultrasonic tomography, UT, very specific application, very promising and very ramping up in the world of non-destructive testing. Very short insight of the measuring principle of any rebar locator. Now, all manufacturers have different arrangement of the different coils that are used to investigate steel, but the basic principle relies on a transmitting coil that is where current is driven in order to generate a magnetic field which induces surface currents onto any electrical conductive body. So we are specifically onto conductive body, specifically ferromagnetic conductive body. When an electrical current runs over an elongated object, we know that a secondary magnetic field is generated. Hence, this is the quantity in terms of voltage that related to the induced magnetic field that it's measured. Quite a complicated measuring principle, but what we care about as NDT users, we know that this quantity, this amount of measured energy is related to concrete cover and the rebar size, and both can be separately calculated. Well, if we move to the other two partners of concrete imaging, both have acting similar principle. They both are based on shooting an impulse into the concrete and listening to its reflected component. Now, the main difference is that a ground penetrating radar will shoot an electromagnetic wave into the concrete, while the ultrasonic tomograph will induce a sonic shear wave impulse. These two kind of energies respond differently when they meet different interfaces. The key point, absolutely qualitative to remember, but it has a dramatic effect on the strength and limitation of each, is that when I shoot an electromagnetic wave, it will partly pass an concrete air interface, while it will totally bounce against a concrete steel interface. When I play with ultrasound, I have to expect an inverse behavior. So all energy is reflected against an air interface, and part of the energy will pass through a concrete steel interface. Now, let's keep in mind that the amount of information that I extract is related to the component that bounces back. So that brings us to the main differences between the two. Steel is the natural target for GPR. Hence, it will be extremely accurate in defining every steel object. Not only, but mainly steel. Air is not a barrier for GPR. Hence, we can investigate through air. It's a good thing. We can have our instrument rolling on wheels. If I have a small air interface, I can bring my insight further to that. Well, if I play with ultrasound, we saw that its kind of energy, ultrasonic waves, tend to pass through steel. So it won't be as sharp on steel, but it will allow my examination to even go further, even dense arrangement, dense rebar arrangement. You can even go past a metal plate and look for an interface behind. Its natural target is air. So everything related with air, may be the geometrical end of the object, may be the smallest delamination, may be an air pocket, a honeycombic, it will be a natural target for ultrasound. For all these kind of techniques, let's keep in mind that what I see best will make me blind behind. So this will reflect later. Eddy current testing it has the great feature of only looking at rebars, so totally insensitive to the material type. Typically, when we're dealing with GPR or PROCEQ, we have to take into account the material properties. Is it wet? Is it porous? How fast is the wave there? None of those complications are there when I simply use a rebar locator, because I only measure a specific target. Concrete cover can be very precise, especially with modern instruments with compensation algorithms. And in fact, it is broadly accepted as the #1 methodology for verifying concrete cover. And as state of the art today, it is the only approach that I can have for having the estimate of a rebar size under lucky circumstances, not under all scenarios, but if there's one guy that can guess a rebar size, it's a eddy current based rebar locator. Now let's turn the medal and let's look at the other side. We said that GPR is a sniper for steel. Okay, if there is too much steel, then I will easily not pass that barrier, and my information will stop. The energy will be highly absorbed by a heavily congested reinforcement. We said that it can pass an air interface. Well, which means that it will be not the most sensitive for small air-based defects, delaminations, and cracks. And its performances go down with conductivity. Hence, let's not expect great performances on fresh concrete. Ultrasonic tomography is a killer for air defects, but everything behind that air defect will be shielded. It will not be the natural, most accurate for measuring single rebars, and it will suffer depth limitations when dealing with porous materials. If I see air and I'm traveling among a bunch of air, then not much room to go. Eddy current is basically limited in depth. We'll see some example, but while a GPR, high frequency GPR can reach up to 60, 70 cm of penetration, ultrasound can go past 1.5 meters, couple of meters in good concrete. With eddy current testing, we are very accurate, but we are talking about centimeters, 10, 15 cm, and only the first mass of reinforcement. Okay, let's see some of this methodology in action, and let's start with first in order of appearance, something that's been on the market since the early 70s, I would say. No comparison between what those instruments could do then and what they can do now, but still, it's very often the #1 instrument that every inspector has in its arsenal. Okay, the very basic output, you can find them in entry-level instruments that when moved on the surface, they can easily locate the rebars, providing the location and not only spot measurement of a given cover and spot measurement of a rebar size. This is the entry-level rebar location that can be used. And it is a central activity in in all NDT inspection. Why? Because a key point of all NDT and traditional testing inspection is that you always want to know where the rebars are, either because you want to measure them or you simply want to avoid them. Of course, you want to avoid when coring and cutting the concrete, but you also want to avoid the effect that they could have on the measurement when performing all other kind of NDT measurements, such as rebound hammer here, such as ultrasound that is affected by the presence of rebars, extraction testing, you name it. Whatever you do on site with NDT, you'll always have to add at least a basic rebar locator. But especially if we focus on high performance instrument, and let's assume you use an instrument with wheel, like the profometer, for example, then you will see that it's really full potential of conformity check for cover. That is a mandatory check in many agencies or many general contractors. You want to check that the rebars have sufficient cover. Perfect. The instrument is optimized for running along huge path, collecting the right cover, and performing on board or on PC the related statistics analysis, which enable the final user to say, my cover is compliant with the draw specification, or we have non-conformities on specific spots. Of course, it can be used for also large investigations, and this is just a way of looking at the data in terms of raw signal. In this case, you could highlight the nuts of the beams with the pillars as seen from the slab, and checking areas with insufficient cover. Same measuring principle can be used for broad slabs or soffits or small elements. These are typical reports that an NDT company could deliver when asked to perform rebar location on single objects. Color-coded mapping in terms of cover or diameter. Just to give an overview of this. But let's move one step further in time, and years passed, and we, the concrete guys, the concrete NDT world, stole what a methodology that was basically born for soil investigation, and hence the ground penetrating radar. If I should label it, the GPR is the ultimate locator. The base, just let's understand very shortly what you have in your hand when you use that. You have a device that you will roll onto a surface along a path. It will send its impulse while running, and it will measure an arrival time of each reflection. The measuring time or measuring distance, once we assume a given velocity, is then represented into an image shape. So with GPR, we move from the simple numbers of a rebar locator to a real image that it's typically in its native raw shape, recognizable by hyperbola-shaped object, just related to the fact that the impulse is continuously measured. And also, it's the key reason why we can see multiple layers of objects. Okay, this was a very simple case. Let's take a look at a real case of a reinforced concrete slab. There are a few meters of scan. We can see the first layer of reinforcement every single rebar in shape of an hyperbola, not only, but the second layer of reinforcement at a given depth. The bottom of the slab, this was a 35 cm slab, and if I focus my sight on the bottom part, I can also see the supporting beam on it. Okay, this scan I wanted just to use to give an first view of the very basic processing that is very common in the GPR world and that it's fully supported in the PROCEQ app, which is the migration. We basically take into account the velocity of the wave into the concrete, and we basically collapse those hyperbolic view into the realistic dots. So a migrated view is the closest thing to a real section of the object that I'm measuring. And I can see dots where the rebars are, top of the slab, bottom of the slab, bottom of the beam, and all the shape of the element I'm investigating. But we can do much more than that. Let's assume that we measure a number of those scans along typically longitudinal, parallel, and orthogonal scans. If I process those data combined and I interpolate the empty spaces, then I can get to a full volume view. That is typically sliced in time. So I move from a distance versus depth view. I move to a more intelligible XY view at the whatever depth I want to reach. And this was made fully available by PROCEQ. This is a kind of processing that's been on for ages now, but I have to admit that PROCEQ was the first one to bring it and to make it onto a very usable interface. So on purpose, I focus on this very typical application that is the heat prevention by means of GPR. So you can see in this fast forward motion that if I scan a small area, the typical 60 by 60 is a good default, I can immediately have an overview, even if it's maybe even complicated. But in this case, it wasn't crucial to estimate all the rebars and to estimate the exact reinforcement, but basically to avoid those. So let's collect all the scans that we need. Let's focus on the surface itself. Every strong reflector can be assumed to be a steel rebar, and I can immediately, or I can, within a reasonable time, I can estimate the right spot to drill a core. That is a very simple example where very high level, what used to consider to be only high level technology, really at hand for very practical applications, such as in this case, we can see a successful coring. So I guess, yeah, that was confirmed on site. Exactly. So good, successful heat prevention, simple case. Okay, moving on to just another short example of a more complex structure. This investigation was taken out to an old building that underwent rehabilitation. So you could really see a mix of old typical structures such as masonry vault and arch that were later reinforced on some portion by some metal reinforcement. Okay, this on the left is just a snapshot at the given depth. The full insight of the whole slab can be gathered by, in this case, a flexible area, so several meters were scanned. And you can really, in this case, the owner of the construction could really directly verify where there was, in this case, the yellow upper metal reinforcement, and where the existing masonry walls on arch in different part of the building. So, in a couple of examples just to touch typical applications, something a little bit more related to infrastructures, just to give an idea that advanced processing can be done even outside the app. There's a software suite that is recently being sold also by PROCEQ. Just to give it the idea that under infrastructures, we'll see the definition of structural details not only covers rebars, but all often and most important post-tensioning ducts. Okay, once we combine all the scans, even in oddly shaped or complex geometries, we can have these volume views that, once sliced, can really provide the insight of the traditional reinforcement and PT ducts. Here an example of the new school slicing under all the possible planes, and the old school detection with raw data and deliverables immediately available or in CAD format. Okay, so much for GPR, and let's look at its successor or its complementary relative. Some of you may already be familiar with some metal testing. Okay, ultrasound in metal testing is often labeled as thickness gauge and flow detector. Okay, in the past decade, the thickness gauge and the flow detector became available for concrete. Hence, we have this tool. Number one, in order of appearance application that I mentioned, is the pure thickness measurement. Not a total chance, but this is an application, the first application in the world that currently has a specific guideline. The German Transportation Agency made it included ultrasonic tomography in order for the checking of the lining, the inner lining of the tunnels. So this, in shape of maps of depth mapping, is one key role and one of the most easy to perform tasks with ultrasonic pulse echo tomography. I won't go back to all the key reasons why small interface are the national target. We already mentioned that into that initial overview. Just wanted to show you a test case that it's quite interesting. This was an artificially induced delamination made by putting a small plastic sheet onto a concrete block. No way you can detect that with GPR. We tried, we know that. But you see the sharpest the draw of that defect by means of ultrasonic tomography. Again, here we have the similar output as GPR. We move the probe onto the surface, distance versus depth. And I have a clear overview of what can be a cold joint, or what can be a corrosion-induced delamination, you name it. Similar feature for a small hair pocket. It was an induced simulated honeycombing. Quite a difficult task even for GPR, especially if it's a small dimensions. You can see that the smallest air interface will reflect sharply on the profile that will see my bottom back wall, so-called back wall reflection, shielded locally by one defect, that becomes a very easy to detect target. And last, but probably among the most important application of PROCEQ, the detection of grouting defects in PT ducts. We know that number one reason for failure of PT ducts in existing structure is corrosion. Now, strands are well protected in a properly injected duct. But whenever, for manufacturing reasons, that quality of injection is not perfect, we open the door for water to filter in and to start eroding the duct. Dramatic effect and this invisible and unannounced collapse at risk. Okay, if I look at these ducts with the GPR, and we saw in a couple of slides before that PT ducts are very well defined by GPR, but the amount of steel is so relevant that will make the GPR blind for any air inside. Well, the only guy having a chance to not being blinded so much by steel and chase after the air portion inside the duct is actually the PROCEQ. So one of the approach, and let's start see on a mock-up case where this partially injected duct was tested inside the lab by means of a line scan, meaning the probe was moved along the axis of the duct by collecting this image that highlights the horizontal reflection of the duct, highlighting a strong portion, because strong reflection for PROCEQ is air. So we see likelihood of being air here, and very likely a properly injected grout PT duct here. Now, when bringing this on-site, this approach, it is quite often preferable to perform the so-called stripe scan. So you are a little bit more sure of centering your duct by several measurements, collecting an aerial overview, a time-slice view, just like GPR did. I collected a number of single scans here, and the app will put together the image, and then I decide to look at this image at the given depth. What depth? The depth where the duct is. And it will provide a more reliable overview of areas where I see a weak reflection of the duct. You see in this portion, this green portion, I see this distance here, which is the same distance that I read here, versus a given depth. And I see that I have a duct at around 12 cm. Well, if I focus on this area, I see that a sharp reflection is confirmed in the line scan. And so if I put together all this information, I will pinpoint the areas of high intensities, and those will be the one where a direct verification will be done. This is a real case where a visual inspection was performed and lack of injection was confirmed. And again, just for jumping back into the slide number 1, it's not that you give up the visual inspection because you own this powerful technological tool. You use the tool to verify the opening on the on the most representative locations. Okay, so much for imaging. Just a short overview of the concrete strength and the homogeneity calculation. I won't dive into the technical details of the tools, but I'll just pick up the two champions of for this purpose, which is ultrasonic pulse velocity, UPV, and a rebound hammer. Now, both methods can provide an estimate of concrete compressive strength. As a matter of fact, a rebound hammer was the #1 in history methodology for concrete strength, dated back in the 60s. When used in combination, they are normally referred as SUNREP, sonical and rebar testing. And if I may add, these quite inexpensive and affordable technologies, they have probably between 80 and 90% of the typical applications of existing structures, so very abundant on the market. Rebound hammer. Basically, the measured quantity they measure is a distance or a velocity of a mass that is projected on the surface. The tougher the concrete, the higher the energy that is reflected. UPV, ultrasonic pulse velocity, I put 2 transducers across the surface and I measure the transit time of that impulse, that typically on an oscilloscope or into a digital interface as it's done today. Okay, so much for details, no time today for that, but the key point that it's normally affecting all the users of the community. Okay, what do I do with this rebound value or velocity values? Okay, 2 levels of approach. First one is just enjoying a qualitative or a comparative information. The second one that I will mention is let's go back to our old school coring and combine the info or both techniques for providing an accurate strength measurement. Case 1. I only measure, in this case, an example of ultrasonic pulse velocity. I can go back to my literature books, I can Google up, and I will find enough qualitative statements. That can be enough for, depending on the purpose, and especially it will enable me to make statements about differences in the structure. Watch out, guys. First floor is for sure a different cost than all the other floors because the velocity is awfully low. Nothing wrong in qualitative information, much better than wrong quantitative information. Another way of using this approach is, a matter of fact, already into a guideline, a national annex of a European standard, which is the general European standard for calculation compressive strength by means of destructive and non-destructive tests. Specifically in the German region, an annex was issued that allows a preliminary conformity check simply by means of the R value, traditional rebound hammer, or Q value, Silverschmidt measurement. So it's a very conservative chart, but if the goal is to verify whether it's compliant to a given characteristic compressive strength, then I'm fine. If it's not, okay, then I will move to the most general approach of combining the direct and indirect testing. As a side note, if I don't have the chance to use calibration, the blind use of literature curve or manufacturer curve is something that is at lack of bringing bad credibility to the method, because it is proven there is no universal curve for rebound value, or even less for ultrasound, and not even for SUNREP method. Here I just, as a reference, I bring a few of them. Try it by yourself. You enter whatever value you want and you'll see a huge spread of values. That kind of spread is often not tolerable for structural assessment for the task. Now, the key point generally for a proper testing, case B that we mentioned, is let's use every tool as its best. So let's take a look at preliminary. Let's use NDT as a preliminary techniques for providing at low cost and in a fast time information on a large number of elements. And let's leave the coring machine on the truck for now. Now, once I collected enough data, now I have the reasons to decide, okay, today in this building, in this hospital, in this structure, I will have reasons to decide to extract, let's say, 5 cores. But now I'm no more blind. If I didn't have this overview, by the way, this is an overview of rebound value and ultrasonic velocities, and I just trusted traditional testing, I might have tested random all the good part or only good portions of the structure. I would have averaged my result and came out with totally wrong conclusions about the structure. Or even the contrary, I could have hit low outliers and classified the structure as to be renovated with huge investment. Now I have selected spots for calibration. I will go on site, I will prescribe a very limited number of direct sampling, and I will have the tools. Now this is just a generic chart, but if I have some pairs of locations where both the non-destructive and the destructive parameter is measured, then I can go to the easiest sheet that I can find and obtain a given regression curve. Once I have that curve, at the cost of a small number of cores, I can recalculate the actual strength that I can use for characteristic strength assessment. That is the idea of the proper non-destructive versus traditional way of testing. This was a very simple sheet, hyperbolic curve. Other curves are possible. If I move into the SUNREB approach, I might have to deal with variables with strength as a function of 2 variables. No reason to panic. Nowadays, even if you're not a MATLAB expert or an Origin practitioner, there are standards tools that can be used, and I went and checked. PROCEQ itself can support calculation of the curves and the handling of those curves into the instrument. So once I have a calibrated curve, I can go straight on site with my Pundit or my rebound hammer and provide an immediate answer in terms of strength. Now, last a couple of words in the last box that I kept. Not last in terms of the importance, quite the contrary. Just a couple of words. Corrosion is the #1 cause of weathering and decay and failure of reinforced concrete structure. Concrete in itself could be almost eternal. Reinforced concrete is not. Why? Because, we will basically touch these 3 key measurements. I'm not saying that those are the only ones. GPR and PulseEcho proved their effectiveness also in the corrosion analysis through the induced products of corrosion, but I wanted to keep this This is the traditional package accepted for the corrosion assessment, and also the easier one to perform without dedicated or customized software tool. So why these three methods? I tried to present it in the most compact way. This is what happens when the corrosion happens when we have corrosion ongoing into the concrete. Basically, we see an electrochemical cell. Iron gets burned by the presence of oxygen, and we see current moving along the rebars and inside the concrete. So if we accept this scheme, we see that we see ionic transportation in the concrete, and that is conductivity is the answer to how good is the concrete in protecting steel. Well, a conductive concrete is not, a resistive concrete is. How much of physical protection is my concrete providing? Well, sir, that is the reason cover meters were invented, and probably that is the reason why your engineers put down a specific minimum cover value, because we know that aggressive agents will permeate, for example, in 10 years will reach the rebars if the cover is 25 mm. If I put a cover of 45, it will last probably 35 years. And last, there's a voltage difference. Okay, we have the tool for chasing after this voltage difference into the surface. So we already covered enough, or at least we mentioned the cover measurement as the eddy current locator as #1 cover measurement. Let's touch a couple of points on resistivity. Electrical resistivity. It has a total dual approach. It is performed both on lab, on the new samples, the same samples that are typically used for compressive strength, nowadays are also being tested for resistivity. The market was led by an AASHTO, American standard, an ASTM followed, and European standard is being worked on. So be prepared, guys. This will be something that whoever deals with testing, even lab testing of materials, will have to take into consideration. In this case, resistivity means how good is the concrete in protecting and avoiding especially chloride ion penetration. That is one aspect of resistivity. The other is, I'm not dealing with a new structure being cast today. I'm dealing with an old bridge, an old structure. I can use this tool to go on site and to evaluate and classify areas where the concrete is still in good or not longer in good conditions for protecting the steel. This is the dual approach of resistivity. While I would say in the #1 technique for global use is the half cell potential, which is the only one telling me, hey, today there is some corrosion ongoing in some specific spots. The physical principle behind is that I chase after this low potential spot indicative of ongoing corrosion, and that can be done by basically a traditional electrical circuit where a hand-end electrode or a wheel electrode are rolled onto the surface. Again, there's no way this will totally avoid traditional opening and visual inspection, but especially on large structure, it will provide a mapping of areas at risk. In this case, you can see a color-coded map obtained by scanning with wheel electrode onto a parking slab. Once these data are processed there are a couple of statistical tricks based on the statistical distribution. It enables the user to provide to the final customer, the contractor, with a red, green, yellow areas that are really maps of priorities. Red area, go, open, and check, and very likely starts putting some money into account for repairing. Green areas, you can save your money, sir, for today. Let's keep an eye and let's monitor this bridge tunnel lining for the next at the next round.